Good morning, this is active filter design, lecture 15. So far we have seen how one might approximate a desired magnitude characteristic in a few different ways. We have covered the Butterworth, the Chebyshev, as well as the inverse Chebyshev approximations. We have also seen how to synthesize equally terminated LC ladder networks which realize these transfer functions. And then we also figured out how one might take advantage of all these all the knowledge that we have developed in the design and synthesis of low pass filters and apply it to other filter types, namely the band pass, the band stop and the high pass cases. And thanks to the use of frequency transformations, one can straight away generate the ladder network corresponding to the band pass, band stop or the high pass cases by simply making the appropriate substitutions in the low pass ladder network. Then we also said that if the low pass ladder is doubly terminated, its sensitivity will be 0 at maxima in the pass band and will be small generally in the pass band where the ripple is small, and therefore it also follows that whatever you do when you transform the network, every reactance is getting transformed to another reactance or a combination of reactances. Therefore, the low sensitivity property will carry over to the band pass, band stop and high pass networks, because the elements in the box, okay, which is between the two terminations, is still lossless. Okay. So another minor point that I wanted to point out is that we've always seen networks of this form where our terminations are 1 ohm and the critical frequency is 1 radian per second. Okay. The only reason for doing this is preventing errors in moving large numbers and so on. So it's always preferable to work with a normalized radian frequency of 1 radian per second and 1 ohm, and 1 ohm is the termination impedance. Of course, in practice it is not likely that you will have omega naught of 1 radian per second and 1 ohm. In general, therefore, what you will have is you would want RT to be the termination impedance to be some RT ohms, okay, and you want the cutoff frequency to go to not 1 radian per second but omega naught. Okay, now let me not confuse you. So I'll say here the cutoff frequency is omega naught is 1 radian per second, and whereas in a practical application you may want the cutoff to be some omega naught radians per second. So given that you know this network, how will I choose the component values in this network? Scale? If you want to keep the cutoff the same and only change the terminating impedance while maintaining the transfer function, all the impedances must be scaled by RT. So what will happen to all the inductors? They will all become L times RT. Okay. What will happen to the capacitors? They will all become C by RT. Now if you want to, so this network as it stands has the same cutoff frequency as earlier, only its impedance has been scaled up by a factor RT. Now if you want the cutoff frequency to move from 1 radian per second to omega naught radians per second, what will you do? You replace S with S by omega naught, which in other words what will happen to the component values? L will become omega naught, and what happens to C? C will also become C by omega naught. So given the normalized ladder network or low pass network or a band pass network for that matter, you can go and derive the network where the cutoff frequency is what you want and the terminating impedance is what you want. The first step where we scaled all impedances by RT is called impedance scaling. The second step where all we did was move the cutoff frequency is called frequency scaling, okay. And following impedance and frequency scaling, you get the appropriate terminating impedances and the cutoff frequencies. All right. Now, if you think about it, and you know, one thing we did see is that if the cutoff frequencies were even in the several hundreds of megahertz range, we saw that the inductor values needed become too high to be practically realizable. Okay, passive inductors become very bulky, and therefore the question of integrating them on a chip when the cutoff frequencies are even several hundreds of megahertz just simply does not arise. And as you can see from this expression, as RT becomes higher, what happens to the value of the inductance? The inductance becomes higher, okay. And why would you, why would you want RT to be high? Why can't, one of you could probably ask me, hey, you know, the value of the big inductances are difficult to realize. So I will make RT very small. If I make RT, I don't know, a milliohm, then the value of the inductance becomes very small, isn't it? So the problem with using very low impedances for the terminating resistors is that the current drawn from the source becomes excessively large, right? So it turns out that you would ideally like to operate with as large an RTS as possible, okay, so that the current drawn from the sources is as small as possible. It turns out that you cannot make RT too large either. The reason for that is, it turns out, as we'll see, that there is something called noise, and if you make RT very large, it turns out that the filter will, apart from filtering the input, will also add its own noise, which becomes too high. So RT cannot be chosen to be very high, okay, and cannot be chosen to be too low, because obviously the sources have to drive this very low impedance. Therefore, often a good choice of RT is necessary, an engineering choice of RT is necessary, where you are neither making RT too large that noise becomes a problem. So you just choose it large enough such that noise is not a problem. Okay, fine. So now that we realize that inductors are for most practical applications, for most practical purposes rather, inductors are not realizable on a chip. The question arises, hey, what can I do to avoid the use of inductors? The only new player I have with me is the transistor, which when biased in the active region behaves like a, or can be made to behave like a voltage controlled current source. And in other words, using transistors we can make in principle all the four control sources. We can make the voltage control voltage source, we can make the voltage control current source, current control voltage source, and the current control current source. So from a network theoretic viewpoint, one might ask, if I had the possibility of realizing ideal control sources, how these ideal control sources can be properly realized using transistors is a completely different matter, right? We know that it can be done. There are probably several ways of doing it, okay, and that's the next level. But the first question I'd like to ask is, if I'm able to realize control sources, then is it possible for me to get rid of inductors in the first place? If the answer to this is yes, then I spend time going and figuring out how to build these control sources using transistors. But there is no point in trying to figure out how to build the control sources using transistors, and then after all this you then figure out that, oh, it doesn't help to have control sources. Obviously, not a smart thing to do. So the first thing to do is, if we had at our disposal control sources of whatever kind we wanted, the question is, can we realize the functionality of an inductor. Okay. And to answer that question, a couple of simple observations. In a capacitor, what is the differential equation governing the voltage across the capacitor and the current to the capacitor? We see the capacitor voltage is 1 over C integral IC dt. Okay. On the other hand, for an inductor, the inductor current is what? 1 by L integral VL of t dt. You understand? I mean, we know the inductor V is L di dt, which is in integral form, what I have written down there below. Correct? So, if you stare at these two equations, what do you fundamentally notice? Both these elements are essentially performing the role of integration. Okay. However, the difference between the capacitor and the inductor is that in a capacitor, the current is integrated and you get a voltage, and in an inductor, the voltage is integrated and you get a current. Okay. So, if you want to make an inductor look like a capacitor, what do you need to do? You could, for instance, take a capacitor and make its current. So, you put a magic box between okay. And what is the magic box job? Its job is to take the capacitor voltage and make it look like a current. Okay. So, let me call this I1. Okay. I1 must be proportional to V2, and if you want to interchange the roles of voltage and current in the capacitor, what will you do? You want to make the capacitor current look like you want the capacitor voltage to look like the input current, and the capacitor current to look like the input voltage. So, in other words, I2 must be proportional to V1. Okay. It is going into the capacitor. Let's see. Actually, okay, it doesn't matter at this point. Okay. I mean, so at this point we just postulate that this is what we need for the box. We'll figure out what to put in the box to make this happen. But if the box does this, then we see that the voltage here V1 depends on I2, okay, and the current I1 depends on V2. So, V1 by I1, correct, depends on I2 by V2. What is I2 by V2? How is I2 related to V2? You understand? V1 is proportional to I2, I1 is proportional to V2. This implies that V1 of S by I1 of S is proportional to I2 of S by V2 of S. And what is I2 of S by V2 of S? It's the admittance of the capacitor, which is S times C. So what we see is that the input impedance becomes related to the admittance of the capacitor. Obviously there must be, I mean, if written, I can't write the equal to, because it will be dimensionally inconsistent, correct? That's why here I only wrote I1 is proportional to V2 and I2 is proportional to V1. This constant of proportionality must have dimensions of Dinesh. You're Dinesh, right? You're Avinash. Who's Dinesh Jayaraman? You're Dinesh Jayaraman. Okay. Yes, Avinash. Conductor. Similarly, conductance. Okay. And obviously, I mean, it's not good to call this conductance, because when somebody says conductance or resistance, what do you understand by that term? When voltage and current at the same port are related by some constant quantity, that constant quantity is called either the conductance or the resistance, right? Now the voltage is at one port and the current is at some other port, so what must you call it? Transconductance. Okay, so these constants of proportionality are fundamentally, you will call them, will have dimensions of conductance, and you call them transconductances, because they relate the voltage at one port to current at some other port. Alright. So this I2 by V2 is nothing but proportional to S. Okay. Alright. So this, and therefore V1 by I1, if it's proportional to S, therefore it looks like an inductor. And given that all that you need is current being proportional to voltage and voltage being proportional to current, what do you think, are there any reactive elements inside the box? So we want, in the magic box, what do we want? This is the notation for a transconductance. Okay. It's understood that this voltage is referred to ground. You can't, I mean, when somebody says the potential of this node is 5 volts, it is with respect to ground, which is not shown. It's a voltage controlled current source, right? The voltage is always measured between 2 points, the other point is assumed to be ground. So if this is V1, okay, and you want I2 to be related to V1, so alright, so what is this current now? GM1 times V1. What is this? And then you want the port 1 current to be related to port 2 voltage. Okay, so what should I do? GM2, okay. All right. Simplistically, I mean, this is basically this. What we had in words earlier is now a picture. That's all. Correct? Let's see what we get. So if this is V1 and this is I1, okay, what is I1? What is V2 first? V2 is nothing but this current is GM1 times V1. What is the voltage? GM1 V1 by SC. Okay. All right. If this is the voltage, what is this current? This current must be, so I1 happens to be minus GM1 V1 by SC times GM2, okay, and therefore if what is V1 of S by I1 of S? What is the input impedance? Zn is nothing but, come on people, why, look carefully, I mean minus SC by GM1 GM2, okay, all right. So it does, it therefore follows that if you want the input, I mean clearly we are getting the S that we want multiplied by some constant which is obviously the inductance, but there is a negative sign. If you want the input impedance to be an inductor, this must be positive. So what can you do? You change the signs of either GM1 or GM2. I will just arbitrarily choose this to be negative, okay, in which case this becomes positive and this current is in this direction, okay, and this becomes.
Sir, I can have the capacitor floating also.
Technically, a voltage controlled current source, a true voltage controlled current source is like this. All right, I have simplified matters, and what I am doing when I join these two and connect them to ground, okay, this is whatever minus GM. So this is Vn, this is GM Vn flowing this side, okay, that's what this means, all right. My plus GM means that the sign of the arrow will be in the opposite direction, all right. So one thing that's clear is that one of GM1 and GM2 must be negative, and so this therefore is the final structure of the magic box. Okay, this, and in standard two port notation, the port currents always going inside. Okay, if you think of this as a two port, all right, I1 is nothing but, what is I1? GM2 V2, all right, and what is I2? Minus GM1 V1. So what is the Y matrix of this magic box? What is Y11? 0. What is Y12? GM2. What is Y21? Minus GM1. What is Y22? 0. Okay. And the job of this magic box is to basically take the port 2 voltage, make it look like port 1 current, and have basically interchanged the roles of make port 2 voltage and current proportional to port 1 current and voltage. Okay. So there is a special name for this box. It's called the gyrator. Okay, it's a 2-port element. It's that special 2-port with this admittance matrix. All right, and clearly, I mean, once you have this box, it doesn't necessarily mean that you must put a capacitor on at that side. You understand? I mean, I have a box, I can do whatever I want with it, right? So if I put a resistance there, what do you think will happen? How will it look on this side?
Negative resistance.
No.
Resistance only.
Shravan Siddharth, what will it look like if I take this box, put a resistor here?
Resistance.
What do you think it will look like?
Another resistance.
It will look like a resistor only. If I put a capacitor, what will happen? Inductor. If I put an inductor, it will look like a capacitor, right? If I put a resistor and a capacitor in parallel, how will it look?
Inductor and resistor in series. Inductor and resistor in series.
The Z looking in here will be proportional to the Y at the Z at port 2 will be Y at proportional to Y at port 1. Okay. So what is Y at port 1? It's G plus SC. It's a shunt combination of two admittances. So the admittance looking in at port 2, I mean terminating port 2 is conductance plus some SC, which means that the impedance looking in here must be proportional to some A plus B times S, right, which corresponds to a resistor and inductor in series. Okay. Similarly, if I put a resistor and inductor in series at port 2, it will look like a capacitor and resistor in parallel. Does it make sense? Okay. All right. All right. So now that we have figured this trick out, let's try and realize a very simple network that we have probably seen in high school physics. It's a second order band pass filter. R, L and C. This is I in. So how does this what is V out of S in terms of the input current Laplace transform? What kind of response is it? Is it a low pass type response, a band pass response, or a high pass response? Band pass. Why is it band pass?
There will be zero. There will be zero at zero.
Pardon? At high frequency, the capacitor becomes a short. At low frequency, the inductor is a short. At some critical frequency, the LC parallel network becomes open. So the impedance kind of is a short at DC and short at high frequency and kind of reaches a maximum somewhere in the middle. So it's a band pass type of response. Okay, what is the actual response? Let's put it in a nicer form. I'll multiply the numerator and denominator with LC. Okay. So V out of S by I in of S let's put the denominator in what is called standard notation. Okay. in circuit work you always keep the denominator such that the constant term is 1. You pull everything out. So, when the denominator is evaluated at DC, you must get 1. So, this is already in that form. Okay. So, standard form for a DFS is always placed in this form 1 plus S by omega P QP plus S square by omega P square. Okay. So, it is always nice to cast whatever you get into this form. Clearly, there are two coefficients LC and L by R, and there are two numbers here omega P and QP. So, it stands to reason that one should be able to derive the values of omega P and QP in terms of LC and L by R. So, omega P is called the pole frequency, all right, and QP is the quality factor. I'll tell you why these terms make sense. So, if you have a denominator like this, can you tell me where the poles are? Where are the poles of the denominator? To find the poles, you said you need to find the roots of the quadratic. So, the roots of the quadratic will be, instead of carrying S by omega P all over the place, I will say S by omega P must be equal to minus 1 by 2 QP plus minus square root of B square okay. So, there are two poles. If QP is less than or if rather if 4 QP square is less than 1, what can you say about the poles? 4 QP square is less than 1. Two real roots, two real poles, and where are these poles? On the in the left half on the negative real axis. Okay, all right. So, this means that 4 QP square less than 1 means what? QP is less than half. All right. If 4 QP square equal to 1, then 2 repeated roots, okay, and if 4 QP square is greater than 1, what do you get? Complex conjugate and how do the complex conjugate poles look? S must be equal to omega P times minus 1 by 2 QP plus minus J square root of 1 minus 1 by 4 QP square. Okay. And what is the radius of these complex conjugate poles? So, as QP keeps changing, please notice that the modulus of these complex numbers remains. Kartikeya, what is the modulus of these poles? What is the modulus of this complex number? Okay, the stuff in brackets is modulus 1, so S has a modulus of omega p. In other words, regardless of QP, these poles lie on a circle whose radius is always omega p. Alright. If Q is greater than half, then but small, the two poles will be here. As QP keeps increasing, the poles move closer and closer to the j omega axis. As QP tends to infinity, you have two poles on the j omega axis. Okay. So as QP tends to infinity, you have poles on the okay. So if a network has poles, or rather if some impedance has poles only on the j omega axis, what kind of network must it be? It must be a lossless LC network. Okay. So if now the impedances are lossy, what will happen? If the inductors and capacitors, real inductors and real capacitors are not lossless, they have some series loss because of resistive effects and so on. So where do you think the poles will go? They'll move into the left half plane. Okay. So this is the motivation. So in other words, the closer the poles of a lossless network are to the j omega axis, right, the better you can say about the quality of these lossless elements. You understand, right? If you have good inductors and good capacitors, they are supposed to be lossless, in which case the poles of an impedance formed using such elements will be on the j omega axis. So it makes sense to say that if the poles are close to the j omega axis, the quality factor of these poles is very high. Okay. And as the quality keeps falling, you see that the poles start to move into the deeper and deeper into the left half S plane. Does it make sense? Ideally, the quality is infinity, then you will have poles right bang on the j omega axis. All right. Okay. So now that we've established this notation, this we'll keep using this over and over again. So now in terms of these element values, can you tell me what omega p is? 1 by root LC. And what is QP? Please decide among yourselves and tell me what is QP. If R becomes large, do you think the QP will increase or decrease? In other words, if R is the ratio of R divided by square root of L by C, so this is omega square by omega p square plus S by omega p QP plus 1. Okay, and how does the numerator look? I can write this as S times okay, if I write this as S by omega p times omega p times L, correct? And what is omega p times L? Root of L by C. You understand? And at omega p, what is the impedance? It is R, okay, and you can see that in two ways. One, of course, is when LC becomes open, the impedance is R. From this expression, when S becomes equal to j omega p, 1 plus S square by omega p square goes away, and the numerator S by omega p cancels off, and you have square root L by C divided by 1 by QP. So QP goes into the numerator, and QP is nothing but R divided by square root L by C. So, the impedance must be R. Okay. All right. So, let us get back. So, this is R, this is C, and this is L. Now, I want to replace L with control sources and capacitors. So, what should I do? Replace let me call this GM2 minus GM1. It doesn't really matter which you make negative as long as one of them is. So let's call this C2 and let me call this C1. All right. All that I have done is replace the inductor with GM2 minus GM1 and C2. Is this clear? Okay. So, now you have a network which, as you can see, has got only control sources, capacitors and resistors. Presumably, the control sources can be made with transistors. So, the control sources can be very, very small and compact, and therefore, you can integrate the whole thing on a chip, and you have gotten rid of inductors completely. Okay. So, this must be, what is this voltage? What kind of response is that? Band pass, because this is an inductor and we already figured this voltage out. So, what will the omega p of this, let me call this VBP, okay, and VBP of S by In of S is nothing but square root of L by C, and what is L? C2 divided by GM1, GM2, okay. So, this is square root of L by C times S by omega P divided by S square by omega P square plus S by omega P QP plus 1, where omega P is 1 by square root LC, which is the same as 1 by square root of GM1, GM2 divided by C1, C2. Okay. And what is QP? Is R divided by square root L by C1, and this must be R under root, what is L? C2 by GM1, GM2, C1, which is therefore R times square root of GM1, GM2 divided by square root of C2 by C1. And as you can see, the QP, which must be dimensionless, is indeed so. Okay. All right. So the next thing is to say, hey, okay. The next thing is to say, hey, everything here seems to be control sources and capacitors other than this character here, right? So is it possible to realize a resistor using a control source? Yes, no? Can I use a voltage controlled current source to realize a resistor?
Yes.
Yes?
Yes.
How?
So the controlled voltage make it a function of the input voltage. The controlling voltage make it a function of the input.
So this is a transconductor,
Yes.
correct? Okay. And if I, let's say it's minus Gm, if I connect the output to the input,
It becomes a
what is the impedance looking in?
1 by Gm.
1 by Gm. Okay, so this is V, this is Gm V. Okay. Is this the convention we used or what? Yeah, I think it is. Okay. All right. So in other words, you don't really need the resistor. If you had controlled sources, you could get rid of the resistor and make everything with controlled sources, and that would look this is minus Gm3, correct? All right. And then the last sore point is that the input is a current. Let's say you don't like it and you say I have only an input voltage, then how can I generate a current by looking at the input voltage? Use another control source. You understand? All right. And so what is VBP of S by Vn of S? What will omega p be? S square by omega p square plus S by omega p QP plus 1. Okay. Omega p will be Gm2 Gm1 by C1 C2. QP will be, all that you have to do is find the earlier expression for QP and replace R with 1 by Gm3. Okay, so this will be square root of Gm1 Gm2 by Gm3 square, okay, times 1 by square root of C2 by C1. Okay. And what happens in the numerator? We earlier had S by omega p times square root of C2 by C1 Gm1 Gm2, okay. But I mean earlier what we had was this I in of S. I in of S is nothing but GM4 into V in of S. So I can make this, okay. So VBP of S by V in of S is nothing but S by omega P square root of C2 by C1 GM4 square divided by GM1 GM2 divided by S square by omega P square plus S by omega P QP plus 1. Right, and you can see clearly that this is dimensionless. All right, and you can, if you saw this for the first time, it would probably seem quite complicated, but now you know how you got it. This is basically taking a second order, I mean RLC parallel network, which you are all very familiar with, and replacing the inductor with a gyrator terminated with the capacitor, and the resistor with a transconductor, and the input current source with voltage source and a transconductance. So all that you see here are transconductors and capacitors. So this way of implementing filters, active filters, are what are called transconductor capacitor filters, or transconductance is GM, capacitance is C, or called GMC filters.
Is there any reason for resistor being replaced?
I mean the only reason is that if you wanted a network with only transconductors, then there's no earthly reason why a GM cannot be realized, I mean a resistor cannot be realized using a control source. You understand? So that now you have, I mean if you take a look at it, if the resistor, if all these control sources are made in the same way, then ratios of these control sources will become very accurate. So QP, as you can see now, is only a function of ratios of like elements. They are all control sources. So if one control source varies with temperature, all of them will vary with the same way. So the ratio remains unchanged. Okay. So and similarly, if C2 varies with temperature, C1 also varies the same way. So say square root of C2 by C1 also remains unchanged. All right. So you see that all dimensionless quantities being only a ratio of like components, dimensionless quantities are very stable on an IC, because all of them vary, but all of them vary the same way. So when you take ratios, they all become quite insensitive to variations in temperature or process. Okay, I'll stop here. We'll continue tomorrow.